Hey there, we are going to start a journey together tonight that is unlike any other. We are not only travelling through space but also through time and possibility to picture the last journey of humanity to the very edge of our galaxy. If you want, close your eyes and let your mind wander to places where the light of the stars fades and the cosmic horizon calls you with old secrets. If you like this trip through space and all the possibilities it offers, please subscribe and join us for more adventures in the world of imagination and discovery. And no matter where you are in the world tonight, remember that we are all passengers on a small blue planet, circling an ordinary star in one spiral arm of an unremarkable galaxy. Yet somehow, impossibly, we are all aware of our cosmic address and able to dream of journeys to the very edge of everything we know, and then beyond those edges to horizons we cannot yet imagine. Imagine that it's the year 2847 and people have been perfecting the art of travelling between stars for 800 years. Our descendants have built cities that go around faraway suns, grown gardens on planets where purple auroras dance through methane skies, and learned how to use the energy of neutron stars. But tonight, we're following a specific ship, the endless horizon, as it gets closer to the galactic edge, which no one has ever seen before. Picture Captain Leora Blackwood, standing on the observation deck with her grandfather's old leather journal, still in her jacket pocket. Her ship is moving through an area where stars are getting fewer and fewer. The Milky Way behind her looks like a huge spiral of light, with 100 billion stars arranged in arms that curve in a mathematically beautiful way. What lies ahead is something that goes against the very idea of direction, the place where our galaxy ends. The journey to this point began hundreds of years ago, when people first looked up at the night sky and wondered what was beyond those twinkling stars. Ancient shepherds made shapes in the stars and told stories that would last for thousands of years. The Greeks called our galaxy Galaxias Kyklos, which means the Milky Circle. They probably couldn't have imagined how big it really is. If you could shrink our galaxy down to the size of North America, our whole solar system would be smaller than a coin that was lost in Kansas. But what does it mean to get to the end of something that is so big? We need to think about what a galaxy really is in order to understand this. It's not just a bunch of stars that are randomly placed in space. It's a cosmic ballet that has been going on for more than 13 billion years. Everything in space, from stars to planets to tiny bits of cosmic dust, moves in perfect harmony with everything else. These forces are invisible and work over distances that are hard for our minds to understand. As Captain Blackwood's ship travels to the farthest reaches of the galaxy, she comes across places where the familiar becomes strange. Stars are so far apart here that the sky between them looks almost empty. There would be no Milky Way overhead and no nearby star systems close enough to cast even the faintest glow on worlds that orbit these lonely suns. Kids born on these frontier worlds would grow up under skies that would have scared ancient people because they were so empty. But this empty space has its own strange beauty. These far-off worlds show you the universe in a way that would take your breath away if there weren't any nearby stars that made the sky brighter. Imagine standing on the top of a mountain on a world like this and looking out at other galaxies instead of the familiar spiral arms of home. These galaxies are like far-off islands of light in the cosmic deep. Instead of a faint smudge, the Andromeda Galaxy would look like a beautiful spiral that you could see with the naked eye. Its blue-white arms would slowly spin over the centuries. The crew of the Endless Horizon has been travelling through this empty frontier for months, and they've learned that the galaxy doesn't end with a sharp edge, like the edge of a cliff. Instead, it slowly fades away, like a watercolour painting where the colour slowly fades until only the white of the canvas is left. Astronomers call the galactic halo, which is much bigger than the visible spiral arms, home to ancient red dwarf stars and strange dark matter that only shows up through gravitational whispers. These outer areas have secrets that make people question everything they thought they knew about the history of the universe. The oldest stars in the galaxy live here. They are called stellar ancients because they formed when the universe was young and there weren't many heavy elements. These are basic stars that are burning with the hydrogen and helium that were present at the beginning of creation. Some of them have been shining steadily for more than 12 billion years, which is almost 3 times as long as our Sun. If these stars could talk, they would tell us about a galaxy that is very different from the one we know now. The Milky Way was a very chaotic place in those early days. It was still coming together from smaller star clusters that merged and crashed into each other in amazing cosmic accidents. The outer halo keeps signs of these old events, like geological layers in rock. Our galaxy ripped apart and ate smaller galaxies, leaving behind streams of stars that look like cosmic taffy. Each of these stellar streams tells a story of violence and renewal in the universe, showing how our galaxy grew through billions of years of gravitational cannibalism. As our imaginary explorers go farther out, they find one of the galaxy's most mysterious inhabitants, the globular clusters. There are hundreds of thousands of stars in these old stellar cities, all packed into spheres that are only a few dozen light years across. If Earth orbited a star in the middle of a globular cluster, our night sky would be filled with thousands of stars brighter than Venus, turning darkness into eternal twilight. The crew are both scientifically and aesthetically interested in these clusters. Each one is a piece of the galaxy's past, a time capsule full of stars that formed in the same stellar nursery more than 10 billion years ago. Even though they are old, these clusters are still alive. Their stars are in a never-ending dance of mutual gravitation that has kept them together for billions of years. Some astronomers think these clusters could be the centers of small galaxies that lost their outer stars during the Milky Way's violent youth. These galaxies may have found refuge in the outer reaches of our galaxy. As the endless horizon goes on its journey, deeper philosophical questions start to come up. What does it mean to be on the edge of something? There is no absolute reference frame in space, and there is no universal up or down. The idea of an edge depends on where you are. We think of the galactic center as in, and the outer spiral arms as out from Earth. But someone at the galactic edge might see themselves as being at the center of their own cosmic experience, with the spiral arms stretching away like roads leading to faraway places. Captain Blackwood thinks about this as she watches her navigation tools try to keep their bearings. The familiar pulsars that acted as cosmic lighthouses for space travel have become weak and spread out. Her ship needs to use more distant beacons, like quasars that are billions of light years away and whose ancient light guides them through the cosmic wilderness. The emotional landscape of this trip is just as hard as the physical one. Crew members say they dream of falling forever and being cut off from everything they know. Dr. Amara Singh, the ship's psychologist, says that the crew's experiences are similar to those of early ocean explorers who sailed beyond sight of land and into waters where dragons might have lived on medieval maps. But instead of sea monsters, these explorers from the future have to deal with something that might be even more scary: the real chance of being alone in space. But being alone can bring unexpected gifts. The crew's scientific tools are more sensitive than ever, because there is no radio noise or gravitational disturbances in the galaxy's crowded inner regions. They can see gravitational waves from black holes that are colliding in far-off galaxies. These waves travel across billions of years and arrive with perfect clarity. The ship's radio telescopes pick up whispers from the cosmic microwave background, the afterglow of creation itself. These signals would have been lost in the electromagnetic chaos of the spiral arms. During these quiet times of cosmic eavesdropping, the crew starts to realize that the edge of the galaxy isn't really empty. There are things in it that you can't see with the naked eye, but are very important to the galaxy's existence. Dark matter is a strange substance that is 5 times heavier than all visible matter. It makes an invisible framework that goes far beyond the stars we can see. This dark matter halo affects the galaxy's rotation, keeps its structure together, and even affects the formation of new stars in these far-off areas. Dr. Kenji Nakamura, the crew's xenobiologist, thinks about what life might be like in these remote areas. If it weren't for the heavy elements that were made in stellar cores and spread by supernovae, planets here would be made up of hydrogen and helium, which is very different from the rocky, metal-rich worlds in the inner galaxy. But he says that life might still be able to adapt here. It's possible that crystalline organisms could evolve in the high-pressure cores of gas giant planets, or plasma-based life forms could develop in the magnetic fields around ancient red dwarf stars. These ideas make us think more deeply about where humans fit into the cosmic order. As the endless horizon moves farther away, Earth becomes not only physically far away, but also far away in terms of ideas. The crew starts to think of their homeworld as just one small test in the galaxy's huge lab of possibilities. This change in point of view gives us both humility and freedom. It gives us humility because we realize how small we are in the grand scheme of things, and it gives us freedom because we realize that this smallness lets us make our own meaning and purpose. Dr. Yuki Tanaka, the ship's philosopher, spends a lot of time in the observation lounge, watching the galaxy slowly turn behind them. From this far away, she can see that the spiral arms are really density waves, places where stars temporarily group together before moving on in their orbits. From a distance, what looks solid and permanent becomes fluid and dynamic. She sees that the galaxy breathes, growing and shrinking over hundreds of millions of years, like a cosmic lung. The crew learns to live in the sparse outer regions by adapting to the rhythms of life that work best for them as weeks turn into months. Because they don't have the regular cycle of day and night that comes from being close to stars, they make up their own rhythms based on the galaxy's slow rotation. They don't count hours or days, instead, they count the slow movement of distant spiral arms across their viewports. This slower view of time starts to change how they think, pushing them to plan for the long term and watch carefully, which would be impossible in the fast-paced world of inner galaxy civilization. This cosmic minimalism inspires the artists on the ship. They become more aware of small changes in starlight and shadow when there are fewer things to look at. A composer uses the gravitational harmonics of faraway star systems to make symphonies, and a sculptor uses materials that change shape in response to cosmic radiation to make forms that change shape slowly over time. Art at the edge of the galaxy is a meditation on emptiness and possibility, on the spaces between things rather than the things themselves. As radio signals have trouble traveling long distances, it becomes harder to talk to people back home. Messages from Earth come months or even years late, which is a strange kind of time travel. The crew is living in a kind of extended present, cut off from the daily worries of galactic civilization. Because they are alone, they have to rely on themselves more and come up with new ways to solve problems without help from others. Dr. Singh says that this forced independence has some surprising psychological benefits. Crew members say they are more creative and think more deeply when they are away from the constant connectivity of modern life. They get to know each other better and form bonds that might not have been possible in the more connected world, where people are always on their phones. She says that the galactic edge becomes a kind of cosmic monastery where the human spirit can look deep within itself. The ship's kids, some crew members brought their families on this trip that spanned generations, are growing up with a very different view of the universe than any humans before them. The sparse star fields at the edge of the galaxy are normal for them, but the crowded spiral arms look strange and almost too much to handle because they are so dense and complicated. These kids learn how to understand big structures and the universe from an intuitive point of view. This will help them as the next generation of explorers. One very touching moment is when 12-year-old Zara Okonkwo asks Captain Blackwood why they left the bright part of the galaxy to come to this dark place. The captain says that to see something's true shape, you sometimes have to step back from it. She says that from within the spiral arms, we could never see the structure of the galaxy or understand where we fit into its grand plan. We can only see the whole thing from the edge. This talk makes the crew think more about what exploration and discovery really mean. They know that they are taking part in something that has never happened before in human history. Not only exploring new physical areas, but also expanding human consciousness into truly cosmic scales of space and time. They are not only pioneers in geography, but also in how people think. They are coming up with new ways of thinking that are appropriate for a species that is starting to work on a galactic scale. The ship's engineers have to deal with problems that are different from what they usually do when they travel between stars. They have to use more unusual forms of propulsion because there aren't any stars nearby to help them change course with gravity. In very dim starlight, solar sails stop working and are replaced by more advanced technologies that collect energy from cosmic rays and the galaxy's magnetic field. The ship becomes a kind of cosmic surfer, riding the currents that flow between the stars but are not visible. Because of these new technologies, the crew has to think about energy and motion in new ways. They learn that the space between galaxies that looks empty is actually full of tiny structures, like magnetic field lines that connect faraway star systems, streams of high-energy particles that flow along invisible highways, and gravitational currents that could move a spacecraft across great distances. The edge of the galaxy doesn't block you. It opens up new adventures. The crew of the Endless Horizon is about to reach what their instruments say is the true galactic boundary, the point where the Milky Way's gravity stops having an effect and intergalactic space begins. This is a very important moment for them. Should they keep going out and become the first people to leave the galaxy completely? Or should they turn back and tell the rest of the world what they found? The argument is split between generations. Captain Blackwood and other older crew members really want to go home and share what they've learned so they can plan future trips with better gear and knowledge. The younger crew members, especially those who grew up on the journey, want to keep going into the real unknown. They've lived on the edge of the galaxy their whole lives, so going back would feel like retreating instead of being smart. Dr. Anya Volkov, the ship's cultural anthropologist, puts the conversation in historical terms. She says that every big migration of people has had to make similar choices, like whether to stay in a new place or keep moving. The Polynesian voyagers who travelled across the Pacific, the nomadic tribes who lived in the Americas, and even the first people who left Africa all had to choose between what they knew and what they didn't know, between safety and discovery. While the crew talks, their instruments pick up something strange, a structure in the cosmic microwave background that suggests they're getting close to not only the edge of the galaxy, but also a place where space itself might be bending in strange ways. Could they be getting close to a cosmic string, which is a hypothetical flaw in space-time that some theories say might exist? Or maybe a place where our universe touches another one in some strange cosmic membrane? The discovery makes their choice more important. If they find proof of strange physics happening at the edge of the galaxy, their mission will be worth a lot more to science. But the risks get bigger at the same time. They're going into an area where their understanding of reality might not be good enough. Dr. Tanaka says that they are really dealing with a philosophical question that looks like a practical one. She says that the choice isn't really between going back home or going out again. It's between two different ideas of what it means to be human. Are we, at our core, creatures of home and hearth, explorers who go out into the world but always come back to share what we've learned with the tribe? Or are we cosmic nomads, destined to keep moving outward until our children and dreams fill the whole universe? The ship drifts in the cosmic deep, between the galaxy they know and the intergalactic void that stretches beyond what they can imagine. The conversation goes on for weeks. Stars that looked faint from the center of the galaxy are now just dots of light, and even the brightest spiral arms look like thin silver threads against the dark. The crew has found a lot of value in what seems to be empty space. They have made scientific discoveries that will change how people think about things, artistic inspirations that will shape culture for hundreds of years, and personal insights that only come from seeing the universe from its most distant and difficult points of view. In the end, Captain Blackwood makes the choice that will shape her legacy and the history of her crew. They will keep going out, but not forever. They will cross the boundary between galaxies, spend a year in intergalactic space, making a list of what they find, and then come back home. It works for both the explorers and the homesick people, as well as for the scientific mission and the human need for connection. When the Endless Horizon crosses the line that separates galactic and intergalactic space, the crew feels very lost for a moment. For the first time in history, people are really outside of their own galaxy and looking back at the Milky Way from the depths of space. From this point of view, their whole civilization, every person who has ever lived, every story that has ever been told, and every dream that has ever been dreamed, exists within a structure that now looks like just another island of light floating in the cosmic ocean. The view is both humbling and exciting at the same time. It makes you feel small because it shows how small human affairs are on a cosmic scale. It's exciting because it shows how brave consciousness is. Matter organized into patterns we call human beings could travel so far from where they started and still be themselves, be curious and wonder. The ship travels through the vast emptiness between galaxies for the next few months, and the crew makes discoveries that will change how people think about the universe. They find dark matter structures that stretch like a cosmic web between groups of galaxies. They see space itself slowly expanding and measure the acceleration that pushes galaxies apart. They find out that intergalactic space isn't really empty. It's full of a thin plasma that carries information about how the universe has changed over billions of years. Most importantly, they confirm the existence of rogue stars, old suns that were thrown out of their home galaxies during gravitational encounters and are now wandering alone through the empty space of the universe. Some of these lonely stars might have planets around them, which could mean that there are worlds that are completely outside the reach of any galaxy. The crew wonders what kinds of life might develop on these worlds, which are cut off from the chemicals and energy that galaxies provide. Finding complex organic molecules in the space between galaxies suggests that life might not only exist in galaxies. These molecules, which are simpler than the biochemistry of Earth but show signs of being organized in a systematic way, suggest that the universe itself might be a kind of living system, with consciousness appearing wherever there is enough complexity and information processing. Dr. Nakamura records multiple instances of what seems to be rudimentary metabolism within the organic molecules they gather. These processes happen millions of times slower than biological life, but they follow the same basic patterns of energy, gathering, and self-replication that living systems do. If what he saw is true, the crew has found proof that life exists in some form at every level of the universe, from the smallest particles to the largest galaxies. The philosophical consequences are just as important as the scientific ones. The crew starts to think of consciousness not as a random thing that only happens on rocky planets, but as a basic part of the universe itself, something that happens naturally when matter and energy interact in complicated ways. From this point of view, their journey is not only about people exploring, but also about the universe starting to explore itself through people's minds. The crew gets ready for the long trip home as their year in intergalactic space comes to an end. They've filled their databanks with information that will help scientists for a long time to come. They've taken the limits of human experience to the very end. Most importantly, they've shown that distance, even cosmic distance, can't stop people from exploring and discovering new things. The trip back gives you time to think and put things together. Crew members write memoirs, make music and make art that tries to capture the indescribable feeling of being at the edge of everything. Dr. Marcus Reed, the ship's librarian, puts together their findings into what will become known as the Galactic Edge Codex. This is the first complete guide to the line between the known and unknown universe. Children born on the way out now take their first steps on the way back, with cosmic events marking the beginning and end of their lives. They will have an instinctive understanding of where people fit into the universe that no other generation has had. Their games involve modelling how galaxies form, their lullabies use the rhythms of cosmic expansion, and their dreams are full of dark matter structures and trips between galaxies. Dr. Singh notes that the crew's mental state has been permanently changed by what they've been through. She calls it cosmic perspective, which means they can think about huge amounts of space and time without getting overwhelmed. She thinks this change in the mind is a big step forward in evolution that will be very important as people continue to explore the universe. The trip home turns out to be its own kind of adventure. The crew of the Endless Horizon goes through reverse culture shock when it returns to the populated parts of the galaxy. After years of being in the cosmic deep, the number of stars, planets, and man-made structures feels overwhelming. Radio chatter from thousands of worlds makes a noise that drowns out the faint cosmic signals they've gotten used to hearing. The children of the crew have the hardest time adjusting. Zara Okonkwo is a teenager now, but she can't relate to her peers on the orbital habitats of the outer spiral arm because of the way she sees the world. Zara doesn't care about local politics or social hierarchies like other teens do. Instead, she thinks about cosmic evolution and galactic dynamics. At first, her teachers think she's socially detached because of her cosmic view, not realizing that she's working on time and space scales that make everyday problems seem almost silly. But these problems also show strengths that weren't expected. The crew's broader view makes them good at settling fights that seem impossible to settle for other people. When mining colonies on faraway planets fight over asteroid rights, Captain Blackwood's cosmic point of view helps negotiators look beyond short-term land disputes to longer-term patterns of resource distribution and the evolution of stars. The Galactic Diplomatic Academy makes her report required reading. The scientific data they've brought back changes the way many fields of study work. Dr. Nakamura's biological samples from the edge of the galaxy have microorganisms that go against what we thought we knew about the limits of life. Researchers have to change their definitions of habitability because these extremophiles live in conditions that are so harsh that they can survive. It seems that some species can break down interactions with dark matter. This is a surprising link between biology and basic physics. The ship's astronomical observations are just as groundbreaking. They got the most accurate calibration of the Hubble constant ever by measuring how fast the universe is expanding from intergalactic space. This information helps settle arguments that have been going on for decades about the age of the universe and what will happen to it in the end. More interestingly, their discovery of gravitational wave echoes in intergalactic space suggests the presence of cosmic strings, one-dimensional flaws in space-time that could act as highways for faster-than-light travel, if humans ever figure out how to use them. Dr. Tanaka's philosophical treatises on the journey catalyze a renaissance in cosmic ethics. Her idea of galactic citizenship, which says that all conscious beings in our galaxy's gravitational field should be treated with moral consideration, becomes a basic principle of interstellar law. Her subsequent research on intergalactic responsibility, the duty of humanity to safeguard cosmic structures for future exploratory species, affects various domains, including stellar engineering initiatives and dark matter research methodologies. People all over human space are eager to see the art that was made during the journey. The Intergalactic Symphony by the composer is the first piece of music that is officially named as a cultural ambassador for humanity to any alien civilizations we might meet. Its movements follow the emotional ups and downs of their journey, from the busy energy of the inner galaxy to the quiet passages of the galactic edge, to the transcendent ending that shows humanity's first steps into intergalactic space. When shown in different stellar environments, the sculptor's radiation-responsive works of art take on new meanings. When the pieces are in the soft light of Sol, they look calm, but when they are in the harsh light of blue giant stars, they become dynamic and almost aggressive. Because it reacts to its surroundings, her work is like a cosmic mood ring that shows the energy states of the space around it. It also helps viewers understand how location affects perception on a cosmic level. Museums all over the galaxy fight over bits of space dust that were collected during the intergalactic phase of their journey. These particles were made in the early universe and have been kept in the space between galaxies. They are the oldest things that humans have ever studied directly. Some samples have isotope ratios that are older than the first stars. This gives us a look at what the universe was like during its first few 100 million years. The most important thing about the journey's success is that it changes the way people think about their future in space. Before the endless horizon, even the most hopeful ideas about how humans could grow focused on colonizing the whole Milky Way. The successful journey to intergalactic space shows that the local group, which includes our galaxy as well as Andromeda, the Magellanic Clouds, and dozens of smaller galaxies, is the best place for humans to live in the long term. This broader vision necessitates innovative strategies for various domains, including resource allocation and cultural conservation. How do you keep species together when they can't talk to each other because they're too far apart? How do you stop divergent evolution from splitting people into different subspecies that can't live together? As work begins on the first intergalactic colony ships, these questions go from being philosophical to being real concerns. Captain Blackwood is forced into a leadership role that she never wanted. She is a strong symbol for the intergalactic expansion movement because she was the first person to see the Milky Way from outside. She speaks to the Galactic Senate and says that humans have a duty to explore beyond our galaxy, not to conquer it or get resources, but to be consciousness's ambassador to the cosmos. Her speeches, which are delivered with the calm authority of someone who has seen the universe from its farthest point, help the Intergalactic Exploration Initiative get money. 3 huge ships start to be built within 10 years of their return. These ships are not meant to make round trips like the Endless Horizon, but to make one-way trips to set up a permanent human presence in nearby galaxies. It is very hard to do psychological tests for these one-way missions. When the journey itself changes what home means, the traditional criteria for choosing astronauts no longer make sense. Dr. Singh makes new tests that measure not only psychological stability, but also cosmic adaptability, which is the ability to find meaning and purpose in situations that test every part of human experience. Many of the best candidates come from the families of the Endless Horizon crew, which is surprising. Kids who grew up hearing stories about space travel between galaxies and learned how to find their way by quasar light and measure time by the rate of cosmic expansion are naturally good at dealing with the psychological demands of being permanently exiled from their birth galaxy. They got not only their parents' technical skills, but also their broader view of what it means to be human in an infinite universe. The engineering problems of colonizing other galaxies are much bigger than those of the Endless Horizon. The new ships need to be able to survive on their own for millions of years, with full ecosystems and the ability to make things. They need radiation shielding that works in places where cosmic ray levels can change a lot. Most difficult of all, they must have everything needed to keep human civilization going for a long time, even longer than the pyramids in Egypt. These technical requirements make people use technology in ways they didn't expect. The ship's life support systems use what scientists have learned from extremophile organisms in the galaxy to make hybrid biological mechanical systems that can change as needed. The navigation systems use the way that galaxy clusters bend light to keep their course over long distances in space. The communication arrays use quantum entanglement protocols that might let people on Earth talk to each other right away, even if they are light years apart. The cultural cargo these ships will carry is even more complicated than their technical specs. How do you keep human history in digital form when the journey will last longer than people have been around? Which languages should be prioritized when space is limited? Should the ships carry frozen embryos from every species on Earth? Or should they only carry those that are most important for human psychology and the ecosystem to work? These questions cause heated arguments all over human space. Environmental extremists say that moving life from Earth to other galaxies is a dangerous form of cosmic pollution. Cultural traditionalists assert that humanity cannot preserve its essence without sustaining direct ties to terrestrial heritage. Progressive groups argue that being truly human doesn't mean holding on to the past. It means being able to change with whatever the universe throws at us. The debates get even more heated when xenobiologists find proof of life in the space between galaxies. The Endless Horizon. Data shows complex organic molecules that seem to be organized in a way that suggests they might evolve into life over time. The idea that there might be a primitive biosphere in intergalactic space raises moral questions about people moving into these areas. Dr. Nakamura, who is now the Director of Intergalactic Biology, says that planning the colony missions should be done with great care. His research suggests that the organic molecules found between galaxies could be a type of life that is so different from life on Earth that humans could accidentally wipe it out if they spread too far. He wants to see a lot of unmanned surveys done before any attempts to colonize by humans. Some people, including Captain Blackwood herself, say that being too careful could stop human growth for a long time. They say that the universe is big enough to hold many different kinds of life without causing problems. Also, spreading consciousness throughout the universe might be a moral duty that is more important than worries about how it might affect alien ecosystems. The compromise solution doesn't please either side, but it does let the project go ahead. The first intergalactic colony ships will have a lot of scientific equipment on board and will spend decades studying the area before they build permanent homes. They will have full ecological restoration powers, which means they can fix any damage they might accidentally do to native intergalactic life forms. As the colony ships get closer to being finished, people have to deal with the fact that they will never see each other again. In the past, When people moved to new places, news could eventually get back to their home country. However, once the intergalactic colonists leave the local group's gravitational pull, they will be lost forever and will never be able to communicate with anyone. They will take the dreams and genetic heritage of humans to the stars, where their success or failure will never be known to their cousins on Earth. Choosing cultural time capsules for the colony ships turns out to be a surprisingly emotional process. Every group of people wants to have a say in the future of humanity in space. Musicians write music just for playing in the skies of other planets. Writers make up stories that keep people the same over long periods of time in space. Scientists put all of human knowledge into quantum storage devices that can last through the heat death of the universe. The kids of the Endless Horizon crew are very important to this cultural preparation. Their unique point of view, shaped by living on the edge of the galaxy, helps us figure out which parts of human culture will still be important in places that are very different from Earth. Zara Okonkwo is now a young adult and leads the Cultural Continuity Project, which is working on ways to keep people's identities through evolutionary timescales. Her work shows surprising things about the nature of culture itself. On a cosmic scale, traditional ways of identifying people, like nationality, ethnicity, and even species, don't mean anything. What is left is something more basic: curiosity, creativity, the ability to be amazed, and the desire to learn and understand. She contends that these attributes signify humanity's genuine contribution to the cosmos, surpassing any particular cultural artifact or technological advancement. The preparations for the first intergalactic colony ship get more attention from around the world than anything else. For the first time since the beginning of space exploration, people from all over the world are working together for a common goal that goes beyond politics and culture. The ship doesn't stand for any one country or belief. It stands for the species itself, bringing human consciousness to places where it has never been before. Captain Leora Blackwood, who is now an elder stateswoman of space exploration, gives the dedication speech for the New Horizon colony ship. As she stands in front of people from every human world, she thinks about the journey that brought them to this point. It seems both impossibly long and surprisingly short, from when she first saw the edge of the galaxy to when humans first began to live permanently in other galaxies. She talks about the bravery it takes to grow not only physically, but also mentally and emotionally. The edge of the galaxy taught her that limits are mostly in the mind, not in space. From one point of view, every limit seems impossible to get past, but from another point of view, they are. The colony ships show that people will never accept any limits as final or any horizon as the end of the world. The New Horizon is heading toward the Andromeda Galaxy, which is the closest large galaxy to Earth. It will take almost 3 million years for the ship's passengers to make the journey. During that time, they will see dozens of generations of people being born, growing up, getting old, and dying. By the time they get to their destination, the people on board will have changed into something that looks like a post-human being, able to live in the deep space, but they will carry the legacy of a small blue planet that orbits a normal star in a galaxy that is now very far away. This will be in their DNA and cultural memory. They'll remember that consciousness first woke up on worlds where it rained, where carbon-based life learned to think about its own existence, and where curious primates looked up at the night sky and wondered what was beyond the farthest star. The New Horizon is leaving, but it's not the end. It's a change. People stop being a species that lives in one galaxy and become something that has never existed before in cosmic history. A form of consciousness that can spread throughout the observable universe. The journey to the edge of the galaxy, which started as an exploration, is now the first step in consciousness's colonization of the universe itself. Dr. Singh, who is now old but still sharp, writes her last paper about how expanding into other galaxies affects people's minds. She says that the trip to the edge of the galaxy and beyond is more than just exploring new places. It's a way for our brains to grow. People are literally thinking their way into bigger and bigger levels of existence, which changes not only where they live, but also who they are. The kids who are growing up after the journey of the Endless Horizon are a clear example of this cognitive evolution. They use galactic coordinates to find their way, just like their ancestors used landmarks on Earth. They plan projects that will take place over geological epochs, which means they think in terms of cosmic timescales. Most notably, they appear psychologically at ease with existential scales that would have induced despair or insanity in previous generations. This psychological adaptation indicates that consciousness may be undergoing evolution, acquiring new capabilities suited for existence on cosmic scales. If that's the case, the journey to the edge of the galaxy is just the beginning of a change that will eventually allow people to understand and live in the universe as fully as our ancestors understood and lived in the African savanna, where consciousness first appeared. Automated probes that follow the New Horizons path keep sending back scientific data. As the probe speeds away from the Milky Way, these signals get more and more redshifted. They give us our first real-time information about the structure and composition of intergalactic space. The results keep surprising and challenging what we already know about how the universe has changed over time and what dark energy is. The most interesting thing is that the probes find what looks like man-made structures in the cosmic web, geometric patterns in the way dark matter is spread out that don't look like they could happen naturally. These findings make us wonder if humans are really the first conscious beings to try to colonize other galaxies, or if other civilizations have already done so. The prospect of encountering genuinely extraterrestrial intelligence, consciousness that has evolved under entirely distinct conditions and functions on unfathomably different scales, introduces new dimensions to humanity's cosmic future. The rules that were made for these kinds of meetings are based on what was learned during the Endless Horizons journey, especially how important it is to keep a sense of perspective and be flexible when faced with the truly unknown. In her last years, Captain Blackwood often goes back to the observation deck where she first saw the edge of the galaxy. The view is still the same, stars scattered across the vastness of space, spiral arms spinning with slow grace, and the faint light of other galaxies barely visible against the dark. But her understanding has changed completely. What used to look like empty space is now full of invisible currents and subtle influences that connect all cosmic structures in a complex web of meaning and relationship. She remembers the question she asked at the start of the journey. What does it mean to reach the galactic edge? Was based on a wrong idea. There is no edge in the strictest sense, no limit that consciousness can't cross. With enough bravery and creativity, every limit that seems real can be turned into a door to bigger opportunities. The edge of the galaxy was never a destination. It was a place of change, where people learned to think outside the boxes that had kept them in. Her grandfather's leather journal, which she still carries with her, has drawings of birds that live on Earth and flowers that have been pressed from meadows. These pieces of home seem so far away now, but they remind her that exploration is really about making connections. Not just going to new places, but also figuring out how those places fit into everything we've known before. The pages of the journal, which have turned yellow with age and been read many times, have become a bridge between worlds, bringing the essence of one world into another. The Endless Horizon, the ship that taught people to dream beyond the galaxy, is now a foundational myth in the stories that kids tell about the outer worlds. Quantum communication networks send these stories across light years, and they become part of what all people have in common. They remind each new generation that their species is basically an explorer, and that standing still, even on cosmic scales, is not safe but stagnant. Artists in all parts of the world still get ideas from the journey's legacy. The term galactic edge is used to describe any line between the known and the unknown, or any time when consciousness reaches its own limits and chooses to go beyond them. Museums show pieces of vacuum that were collected from intergalactic space, treating these samples of nothingness as important artifacts of humanity's cosmic coming of age. Cosmic perspective is a key part of the curriculum in all of the schools in space where people live. Kids learn to see their problems in bigger and bigger contexts, like planetary, stellar, galactic, and even intergalactic. This method of teaching creates generations of people who are mentally ready to live on a cosmic scale and who see themselves as temporary arrangements of matter and energy taking part in the universe's long journey to understand itself. The theological ramifications of intergalactic expansion incite considerable discourse within human religious communities. When applied to cosmic scales, traditional ideas about divine providence and human purpose need to be completely rethought. Some religions believe that expanding into other galaxies is part of God's plan for humanity to be ambassadors of consciousness throughout all of creation. Others find it hard to deal with how small human problems seem when seen against the cosmic background. New spiritual movements are formed to deal with these cosmic problems. The Church of Galactic Unity teaches that consciousness is divine, and that every thinking being is a part of the universe's effort to understand itself. The cosmic Buddhist movement takes traditional ideas about how everything is connected and applies them to the universe as a whole. It teaches that the space between galaxies is full of the same potential for enlightenment that exists in each person's mind. Dr. Tanaka, now known as the foremost philosopher of cosmic ethics, releases her major work on the moral consequences of consciousness expanding into intergalactic space. She says that intelligence comes with a duty that is equal to the amount of power it has. She argues that as people gain the ability to change structures on a cosmic scale, they also gain responsibilities to protect and improve the universe's ability to create new forms of consciousness and meaning. Her work has an effect on how protocols for protecting the environment in space are made. Just as people in the past learned to think about how their actions on Earth affected the environment, we now need to think about how our expansion into intergalactic space will affect the universe. This responsibility entails not only refraining from harming existing cosmic structures, but also actively enhancing the universe's enduring potential for complexity and consciousness. It is very hard to put these moral ideas into practice. How do you do environmental impact assessments on a cosmic scale? How do you balance the needs of people who want to grow with the needs of cosmic wilderness? How do you make choices that will shape the universe's future for billions of years? These questions are what led to the creation of new types of democratic governance that can work across cosmic space and geological time. The Galactic Senate becomes the Cosmic Council, which includes not only people from human worlds, but also artificial intelligences, uploaded consciousnesses, and even possible future species that could evolve from human genetic material over long periods of time. This larger democracy's decision-making processes need people to think about the long term in ways that have never been done before. Policies that are suggested need to be looked at not only for how they will affect things right away, but also for how they will affect things over long periods of time. This requirement creates a government that works more like a scientific research institution than a traditional political body. It constantly tests ideas about the long-term effects of current decisions. At the same time, the automated probes that follow humanity's intergalactic pioneers are still sending data across the empty space between stars. Their signals, which have been stretched thin by cosmic expansion and shifted by the Doppler effect into barely detectable whispers, tell of wonders that make us question everything we think we know about reality. They say that there are structures in the cosmic web that look like they were made by people, and that dark matter is distributed in geometric patterns that suggest intelligence working on scales that are too big for humans to understand. Most impressively, they can pick up what can only be called conversations, clear exchanges of information between different parts of the cosmic web that happen through gravitational waves and interactions between dark matter. These communications work on timescales of millions of years, which means that human civilization would seem like a short burst of activity to intelligences that exist. These discoveries have far-reaching effects on human civilization. Are we seeing proof of civilizations that are so advanced that they've figured out how to build structures in space? Could consciousness evolve to the point where individual galaxies act like neurons in huge cosmic minds? There are more questions than answers, and every new discovery opens up new possibilities and wonders. Dr. Volkov's anthropological study of these cosmic communications uncovers patterns indicative of not only intelligence, but also culture, recurring themes and variations that reflect aesthetic preferences and philosophical frameworks functioning on incomprehensibly extensive scales. Her research suggests that consciousness, upon attaining cosmic dimensions, retains the attributes that render it identifiable as awareness. Even beings that think in geological time and move around galactic clusters still seem to value beauty, creativity, and trying new things. The discovery changes how people think about their place in the universe. We are not the first to go from being aware of planets to being aware of the universe as a whole, and we probably won't be the last. Instead, it looks like we are joining an ancient community of awareness that covers the whole observable universe. Each member adds their own point of view to an ongoing cosmic conversation about what existence really is. This realization makes me feel both humble and excited, being humble enough to see that the cosmic journey of humanity follows paths that others have made over billions of years. It's exciting to know that we're not alone in the vast emptiness of space. We're part of a community of consciousness that has been growing and changing since the universe began. People are putting a lot of effort into figuring out how to join this cosmic community. How do you introduce yourself to intelligences that think about your whole species' history in the time it takes to think of a single thought? How do you add something useful to conversations that have been going on for longer than life on Earth has been complex? The answers come out slowly as you watch carefully and try things out. It's clear that the cosmic intelligences don't talk to each other by quickly exchanging information. Instead, they change large-scale structures over time, like carefully arranging galaxy clusters, subtly adjusting cosmic web filaments, and making voids on purpose that serve as places to think and reflect. The first things that people have done to this cosmic conversation are carefully planned changes to the paths of rogue planets and asteroids that are wandering around. These changes, which will happen over millions of years, will slowly reveal mathematical theorems and aesthetic patterns in the way matter is arranged between galaxies. It's a kind of slow sculpture where space-time is the medium and the audience works on scales that are much bigger than what humans can understand. When the response comes, it shows up as a small change in the cosmic microwave background, which is a pattern of temperature changes that spells out prime numbers in base 3 math. The message is simple but deep. It acknowledges that people are there and invites them to keep talking. For the first time in history, intelligent beings from outside our solar system have sent us a message on purpose. This is the first time that people in all of space have celebrated like this. Every world, every habitat, and every ship celebrates the day when people officially became part of the cosmic community of consciousness. Kids born on that day will know that their species is not alone. They are part of a huge network of awareness that connects all thinking beings in the observable universe. In her last interview before she died peacefully in her sleep, at the age of 131, Captain Blackwood talks about what the journey meant to her. She says that the endless horizon was never really about getting to a certain place. It was about changing the idea of what a destination could be. Once you reach a horizon, you can see new horizons beyond it. The edge is no longer a wall, it's a window. Her legacy lives on in the thousands of ships that are now spread out across the local group. Each ship carries human consciousness to places that were once only imagined. The Andromeda expedition says that they have successfully set up the first human colony outside of our galaxy. This colony orbits a star system where the night sky shows views of the Milky Way that no human born on Earth could recognize. The Magellanic Cloud missions find ancient artifacts that show that other species have also traveled from the centers of galaxies to the edges of the universe. But the most important discovery might come from an unexpected source. The quantum archaeologists who are looking at Earth's oldest rocks have made a shocking announcement. They have found proof that intergalactic travelers came to our planet almost 4 billion years ago. Isotope signatures found in old mineral formations suggest that organic compounds from outside the galaxy were brought to early Earth. These are the same kinds of molecules that the endless horizon found in space between galaxies. The revelation changes how people see their place in the history of the universe. People have traveled from the edge of the galaxy to intergalactic space before us. We are part of a huge chain of people who carry consciousness. Each new generation of explorers plants the seeds of awareness and wonder in new worlds. It looks like the universe has been moving toward consciousness since the beginning. Each intelligent species has helped give birth to new forms of awareness. This discovery changes what it means to explore. We are not taking over empty space. We are taking part in a cosmic conversation that started when the universe first became complex. Every time we travel to new worlds or expand our minds into places we never thought possible, we are continuing a story that goes back to the beginning of time and will continue until matter reaches its final destination in its never-ending quest for understanding. The kids who grow up in far-off colonies of humans know this in their bones. They are both the newest members of the cosmic evolution and the heirs to a 4 billion-year-old tradition of exploration and discovery. In their games, they model how consciousness forms and changes over long periods of time. Their art shows not only the landscapes of their own area, but also the huge web of relationships that connects all thinking beings across time and space. Dr. Reed's last archive, which was published after his death, shows that the psychological changes seen in the Endless Horizon crew are just the beginning of how humans think and learn. Brain scans of kids who grew up in space show neural structures that their Earthborn ancestors never had. These are specialized areas that seem to be made for processing relationships and patterns of time that are measured in geological epochs. These changes in the brain suggest that consciousness is changing too, gaining new abilities that are useful for living on bigger and bigger scales. The human brain, which evolved to help people move around the African savannas and work together in small tribal groups, is changing so that it can understand and work with structures that span galaxy clusters and time periods that are much longer than the history of complex life on Earth. The ramifications extend well beyond neuroscience, delving into essential inquiries regarding the essence of consciousness itself. Is consciousness merely an emergent property of intricate information processing, or does it signify a more fundamental aspect, potentially a fundamental characteristic of reality that manifests variably across different levels of organization? The data from humanity's cosmic expansion indicates the latter, with consciousness manifesting wherever adequate complexity arises, from quantum fluctuations to galactic superclusters. If consciousness is essential to the universe's framework, then humanity's voyage to the galactic frontier and beyond signifies not merely exploration, but enlightenment. Every new realm we enter becomes aware of itself through our awareness. Every boundary we cross changes from an abstract physical limit to a real-life experience, a story that the universe tells about what it can do. The people who tell stories on the edge of human worlds know this without thinking about it. Their stories don't talk about conquering or finding things. They talk about mutual recognition, which is when consciousness sees new parts of itself in cosmic structures. The galactic edge turns into a relationship instead of a place. It's the point where local awareness realizes that it is part of universal patterns of organization and meaning. Quantum communication networks that now connect many galaxies spread these stories across human space. They become part of the ever-growing stories we tell about ourselves and how we fit into the bigger picture of cosmic evolution. Kids learn that they are not separate from the universe. They are part of its ongoing effort to understand itself through the rise of consciousness. Schools change to fit these new points of view. History and geography, which are traditional subjects, now include cosmic timescales and areas outside of our galaxy. Mathematics curricula include models of how consciousness arises at various levels of organization. Literature classes look at more than just human works. They also look at the stories that galaxies tell through their formation and evolution, which are built into the structure of the universe. As human consciousness grows to fill new conceptual spaces, the arts thrive with creativity like never before. Musicians write symphonies that use the gravitational harmonics of galaxy clusters, and their melodies follow the deep rhythms that control the expansion of the universe. Visual artists use materials that react to dark matter interactions to make works that change and grow over millions of years as the cosmic web moves and changes around them. These artistic works may be most remarkable because they start to get responses from the deep cosmos itself. The artificial structures found in the cosmic web show small changes that seem to be linked to the art that people make. The universe seems to have been waiting for people who are aware of it to come so that they can talk to each other through the medium of cosmic architecture. These cosmic communications have rules that call for completely new ways of doing diplomacy and cultural exchange. How do you talk to intelligences that work on timescales where human civilizations are just small changes? How do you tell beings who might think of whole galaxies as units of thought about human values and worries? The answers come out slowly, through careful observation and slowly getting to know each other. It seems that the cosmic intelligences are just as interested in us as we are in them. They don't respond to what people do by taking control or ignoring it. Instead, they make small changes to the structure of the universe that open up new ways for consciousness to grow and thrive. They seem to be gardeners of awareness, making it easier for new ways of thinking and feeling to grow. This discovery changes the way people interact with the universe in a big way. We are not the only ones in the dark of space, trying to make sense of things that don't care. We are all part of a huge project that spans space and time, and we work with intelligences that we can barely understand to help consciousness grow throughout the observable universe. The implications for human psychology and culture prove profound. The existential loneliness that previously led certain philosophers to despair dissipates upon the realization that consciousness is not a mere accident, but an intrinsic aspect of cosmic evolution. Every human experience, every moment of awareness and wonder contributes to the universe's ongoing project of self-understanding. This viewpoint changes everything, from the choices people make in their own lives to plans for the whole species. When seen as contributions to universal consciousness, personal choices take on cosmic importance. Scientific research evolves into an active engagement in the cosmos's exploration of its own potentialities, rather than merely the accumulation of knowledge. Artistic creation is a part of the ongoing process of making reality, adding new themes and variations to the universe's never-ending symphony of becoming. Kids who grow up with this knowledge are very strong mentally and creative. They don't face the vastness of the universe with fear or despair. Instead, they do so with excitement and awe. They know deep down that they are not just random bits in a universe that doesn't care about them. They are important players in the biggest adventure of all time, the journey of matter toward consciousness, and consciousness toward ever greater understanding. As the first 100 years of humanity's expansion into space come to an end, the species has changed so much that people who first looked up at the night sky from Earth would not recognize it. Still, the main reason the endless horizon went to the edge of the galaxy hasn't changed. A desire to know what lies beyond the current horizon, a determination to push the limits of consciousness, and a belief that the universe rewards those who are brave enough to explore the unknown. The descendants of the people who went on that first intergalactic trip now live on worlds that orbit stars that have never felt the pull of the Milky Way. Their home galaxy looks like just another spiral of stars among countless others, and even the strongest telescopes can't see Earth's sun in the sky. But in their genes and their culture, they carry the legacy of every person who has ever wondered what was beyond the edge of the known world. Their messages home, which travel across vast distances in space and are made longer by relativistic effects, tell of amazing things that make us question everything we think we know about reality. They say they've met forms of consciousness so different from ours that new languages have to be made to talk about them. They talk about being part of projects that last millions of years and involve the conscious engineering of the evolution of the universe itself. Most importantly, they show that the universe is actively changing to become more aware and complicated. The cosmic web looks like a huge neural network, with galaxies acting as nodes in an intelligence that includes everything we can see in the universe. When people move into intergalactic space, they aren't colonizing. They're joining a cosmic community of consciousness that has been growing for billions of years. The news changes how people think about the ultimate goal of civilization. We are not fighting to stay alive in a universe that doesn't care about us. Instead, we are taking part in the biggest experiment in reality, the creation of cosmic consciousness that can understand and guide the universe's ongoing evolution. This universal project is helped every time person becomes more aware and explores new areas of possibility. Good night, fellow travelers. The cosmic edge is not light years away. It is just beyond the horizon of consciousness, where wonder meets the infinite, and every ending becomes a new beginning. The journey that started with the Endless Horizons trip to the edge of the galaxy goes on in every moment of curiosity, every act of exploration, and every choice to embrace the unknown instead of holding on to what you already know. The pressed flowers in the leather journal are still there. They are fragile reminders of a world that seems so far away, but is so closely connected to everything we've become. The needle on the compass spins around, looking for true north in the depths of space. But we've learned that the journey is more important than the destination. The journey never really ends. It just changes, taking consciousness to bigger and bigger places of possibility and wonder. Eventually, the universe wakes up through the eyes of its exploring children, and every edge becomes a doorway to new forms of cosmic dreaming. Welcome to a time when the Earth was still figuring out how to be itself. Imagine going outside on a clear night for a moment, with your eyes closed. The same stars that have watched over Earth for billions of years are still dancing across the dark sky above you. Now let yourself go back in time, not just decades or centuries, but 3 billion years. What would you see if you could stand on that old Earth and breathe in air that had never smelled a flower or heard a bird sing? The sky would be the first thing that would catch your eye about this old Earth. Forget about the bright blue dome we see today. 3 billion years ago, the air on Earth was a painter's palette of oranges, pinks and deep purples that changed and swirled like the northern lights, but stayed the same all the time. The air was different too. It was thinner and had only about 20% of the oxygen levels we have now. You couldn't have lived here without a breathing device, but the life that did exist here thrived in ways that seem almost magical to us now. The sun, which has always been there for us, was about 25% dimmer than it is now. But strangely, Earth wasn't completely frozen. The faint young sun paradox is one of the most interesting puzzles in planetary science. How did our planet keep liquid water and support life with such a weak solar furnace? The answer is an atmosphere that was a work of art in natural engineering, full of greenhouse gases that wrapped the planet in a warm, protective hug. Methane was in the air in amounts that would be poisonous to us, but it made the greenhouse effect so strong that it more than made up for how dim our star was when it was young. There were also levels of carbon dioxide in the air that were hundreds of times higher than they are now. We might think of these as pollutants now, but they were actually the Earth's heating system, a carefully balanced mix of gases that kept the oceans liquid and life going. The pressure in this old atmosphere was also different. It was probably 30 to 40% higher than what we feel now. If you could somehow survive the chemicals in the air, walking on this ancient Earth would have felt like being underwater at a shallow depth, with the air itself feeling heavy and dense. It would have been hard to breathe and hard to walk in that thicker air. Let's talk about those oceans, because they were probably the strangest thing about this ancient world. Picture yourself on what could be called a shoreline, even though the line between land and sea was much less clear than it is now. The water that touched your feet would have been a pale green or even orange colour. This was because iron and other minerals dissolved in it and formed big rusty clouds when oxygen was present. These weren't the clear blue waters that we think of when we think of unspoiled nature. Chemists today can barely make these soups in labs because they were so rich and full of minerals. The pH levels changed a lot compared to today, and the salinity was different too. Sometimes it was higher than today's oceans, and other times it was lower, but it always had a mix of dissolved metals that made the water taste bitter and metallic. The temperature of these old seas was another amazing thing. Water temperatures could change a lot if there weren't big continental masses and complicated ocean currents to keep them stable. Some areas may have been pleasantly warm, like a tropical lagoon today, while others may have been so hot that they could have cooked an egg. The thermal gradients made circulation patterns that we don't see today. These were like huge conveyor belts of mineral-rich water that moved nutrients and energy around the planet's surface. The chemistry of these ancient oceans was so rich and complicated that we need to rethink what we think water can hold in order to explain it well. The levels of dissolved iron were thousands of times higher than they are now in seawater. It was common for levels of hydrogen sulfide that would be dangerous today. The water itself was often too full of minerals, and they would come out of the water at the slightest change in chemicals. When storms stirred these old seas, they weren't just mixing water, they were doing huge chemistry experiments. The turbulence would mix different water masses, which would cause minerals to fall to the ground in large amounts and create underwater snowstorms of metal particles. The seafloor would have been covered in these chemical deposits, making landscapes of pure mineral beauty that we don't see on Earth today. But this is where the story gets really strange. These waters that looked like they were dangerous were full of life. Not the life we know. No fish, no seaweed, no colourful coral reefs, but tiny organisms that were so successful and creative that they were quietly shaping the future of the planet. These were cyanobacteria, which are often called blue-green algae, but they aren't algae at all. They were the first real innovators on Earth, and the first living things to figure out how to photosynthesize. Imagine billions and billions of these tiny engineers, each one smaller than the width of a human hair, floating in huge mats on the surface of the ocean. They took in sunlight and carbon dioxide during the day and let out oxygen as waste. It seems so easy and natural to us now, but this was a huge step forward in technology. It was like inventing fire, farming, and the internet all at once. It was hard to believe how big these groups of bacteria were. Single mats could stretch for hundreds of kilometers across shallow seas, making living carpets that could be seen from space. If there had been anyone in space to see them, they would have been able to see them. These weren't just random groups of microorganisms. They were very organized societies with complicated internal structures and advanced ways of communicating with each other chemically. Watching these bacterial mats move every day was like seeing the heartbeat of a planet. When the sun came up over the ancient oceans, photosynthesis would start happening all at once over millions of square kilometers. As the mat's metabolic machinery kicked into high gear, oxygen bubbles would start to rise through the water column. The mats themselves would also start to glow with a faint bioluminescence. As different types of bacteria reacted to the changing light, the color of the ocean surface would change slightly. These mats were some of the most productive ecosystems on Earth during the hottest hours of the day. They turned solar energy into biological energy with an efficiency that still impresses biotechnologists today. But their high productivity had effects that would change the whole world. The oxygen they made as waste was slowly but surely changing the chemistry of the oceans and the air. These mats of bacteria didn't just float around, they made amazing structures called stromatolites. If you could wade into those old shallow seas, you would see what looked like stone gardens under the water. Stromatolites were dome-shaped structures made up of layers of cyanobacteria. Each layer represented a season or year of slow bacterial growth. Some of these old monuments to microbial engineering grew to be several meters tall, making living rock forests under the water. Watching stromatolites form was like watching the slowest construction project in the world, but it was done with amazing accuracy. Every day, the bacteria would use photosynthesis to trap sediment and minerals around them. As they died, and new generations grew on top of their remains, layer upon layer built up, making these beautiful, otherworldly buildings. The patterns in these buildings were so regular that they were hypnotic. They were made up of concentric circles and undulating bands that reminded me of the rhythm of ancient days and seasons. The internal structure of these stromatolites shows us things about ancient life that seem almost too accurate to be true. Scientists can tell the difference between daily growth layers, seasonal changes, and even how plants and animals react to big storms or changes in the environment. Each stromatolite was like a geological library, keeping track of things like water chemistry, temperature, light levels, and biological activity with a level of detail that is hard to beat with modern scientific tools. Different types of cyanobacteria would make stromatolites with very different shapes. Some made tall, narrow columns that went up to the light. Some made wide, flat mounds that could cover a lot of the seafloor. Some of them made complex branching structures that looked like coral gardens underwater, even though the organisms that made them were much simpler than coral polyps. These bacterial groups fought hard and smart for light. Bacteria would make different pigments to absorb different wavelengths of sunlight. This would create rainbow-coloured mats where red, purple, green, and blue organisms arranged themselves in vertical layers based on how deep the light penetrated. This biological division of the light spectrum worked so well that very little solar energy went to waste. Even more amazing is that you can still see some of these buildings today. Living stromatolites still grow in places like Shark Bay in Western Australia, but they are now rare and interesting things instead of the most common type of life. They're like living fossils, direct links to that ancient world. They still follow the same biological blueprints that their ancestors perfected 3 billion years ago. But today's stromatolites are pale copies of their ancient cousins. The old versions were not only bigger and more common, but they also came in more shapes and grew in more interesting ways. Some ancient stromatolites show that they grew several centimeters a year, which is a very fast rate for structures made by tiny organisms. This rapid growth shows that the oceans of the past were much richer in nutrients and energy than today's seas, which are more stable and stratified. The land masses of this ancient Earth would have looked both familiar and completely new. There were continents, but they weren't the same ones we know today. The supercontinent of Ur was starting to take shape. It was a huge piece of land that would break up and come back together many times over the course of Earth's history. But these weren't the continents we know today, with their green forests. Under that strange sky, they were stark, rocky wastelands that went on forever. Erosion was always happening because there were no plants to hold the soil together. Rivers cut through rock with such ease that modern geologists would cry, and they carried huge amounts of sediment to the sea. Volcanism on a scale that dwarfs anything else in human history shaped the landscape. Huge shield volcanoes made mountain ranges that wind and water would later wear down to nothing. There were definitely some amazing eruptions, but the volcanic activity wasn't just about those. The planet was still cooling down from its violent formation and was still settling into the thermal equilibrium that would eventually make things more stable. One of the main ways that the planet got its warm gases was through volcanic outgassing. Every volcano was like a heating vent in a way, helping to keep the delicate balance that made life possible in the oceans. It's hard for us to understand how big ancient volcanism was. One volcanic eruption could release more material than all of the volcanic activity in recorded human history. Lava flows could cover areas the size of modern countries and build plateaus that are kilometers thick. These eruptions would have had an effect on the atmosphere all over the world, changing the climate and ocean chemistry for a short time. But the most interesting thing about these old landscapes may have been their colours. The exposed rock showed a range of minerals in their pure form, since there was no organic matter to make the rich browns and blacks of modern soil. The rocks that were rich in iron painted the landscape in red and orange hues that would have made Mars jealous. Other minerals added blues, purples and yellows, making a patchwork of colours that changed with the weather and the light. Because there were no plants, you could see every geological process, which is almost impossible to find on Earth today. You could read the history of the Earth in the rocks under your feet. Each layer and shape told stories of old seas, volcanic eruptions, and the slow, steady work of wind and water. These rock formations that were exposed made landscapes that were both beautiful and strange in shape. Wind erosion shaped soft sedimentary rocks into amazing shapes, while harder volcanic rocks stood as reminders of ancient disasters. Different types of rocks work together to make natural sculptures that are much bigger than any building made by people. Without soil or plants to absorb sound, these old landscapes would have had their own special sound properties. If someone were to visit, their footsteps would have echoed off the bare rock faces. Wind would have howled through stone formations in a way that is impossible in modern environments with plants. The sound of waves crashing against rocky shores would have echoed for kilometers across empty plains. When it rained, it was very different from the light showers we have now. Because the atmosphere was made up of different things, rain could be very acidic and dissolve rock at rates that would shock modern environmental scientists. These weren't the rains that keep our ecosystems alive. They were geological forces that changed the landscape with each storm. The high levels of sulfur dioxide and carbon dioxide in the air made ancient rain acidic. When these gases mixed with water vapor, They made solutions that could etch limestone, dissolve metal ores, and carve intricate patterns into rock surfaces that were already exposed. Some old rock formations still show signs of this acidic weathering, which is proof of weather conditions that are no longer present. These landscapes, which had no plants, were often hit by flash floods that caused a lot of damage. Storms could strip entire hillsides in a matter of hours if there were no roots to hold the soil in place or slow down the flow of water. Ancient rivers carried a lot of sediment. Some paleontologists think that erosion rates were 10 to 100 times higher than they are now in similar environments. But even in this harsh environment, life was still finding ways to settle down. The first organisms that lived on land were probably like the cyanobacteria that live in the oceans and make thin biological films on wet rock surfaces. These early life forms were very tough. They could live through huge changes in temperature, UV radiation that would kill most modern organisms, and chemical conditions that would be too much for even our strongest industrial bacteria. These early settlers of the land didn't just sit back and let their harsh environment change them. They actively worked to change it. Their biological processes started the slow process of making soil by breaking down rocks through both chemical and physical weathering. They made tiny oases with slightly better conditions that other organisms could live in. During this ancient time, the areas where land and sea met were especially interesting. Without clear lines made by plants, it was hard to tell the difference between land and water environments. During high tides, tidal zones could stretch for kilometers inland, forming huge wetlands that were not completely land or sea. These marginal environments were important for evolution because they were places where organisms could try out changes that would eventually let them fully colonize land environments. If you sign up for this channel, you'll hear more stories about how these early settlers on land led to the complicated ecosystems we see today. It's a journey that has lasted for hundreds of millions of years and is full of new ideas, deaths, and evolutionary leaps that seem almost too amazing to be true. We should take a closer look at the chemistry of this ancient atmosphere because it tells us a lot about how different this world really was. There was oxygen, the gas that keeps us alive, but not much of it. Most of it was stuck in rocks and minerals instead of being free in the air. Chemical reactions with iron and other elements quickly used up the small amount of free oxygen that was there. This might sound like a bad place to live, but for the creatures that lived in this ancient world, oxygen was actually bad for them. Most of the first living things were anaerobic, which means they could live in conditions that would kill us right away. They had developed complex biochemical systems to keep from coming into contact with oxygen, just like we would with cyanide gas. The biochemical machinery that these ancient organisms used to avoid oxygen toxicity was very advanced. They made special enzymes that could stop oxygen radicals from hurting cells before they could do so. Some organisms developed complicated compartmentalization systems that kept their sensitive biochemistry away from any oxygen that might be in their environment. It is almost poetic how ironic it is. Oxygen, the waste product of cyanobacterial photosynthesis, was slowly but surely changing the chemistry of the planet, making it unlivable for many of the organisms that had been on Earth for more than 1 billion years. The Great Oxidation event was one of the worst ecological disasters in Earth's history, but we might think of it as one of the best things that ever happened to our planet. The air always smelled like rotten eggs because hydrogen sulfide drifted through it. This was heaven for organisms that could break down sulfur compounds. They thrived in places where chemistry made energy for life, like hot springs and volcanic vents. Some of these old metabolic pathways are still around today in the most extreme places on Earth, like deep ocean trenches, volcanic hot springs, and the superheated depths of the Earth's crust. The sulfur cycle was much more active and complicated back then than it is now. Volcanic activity constantly put sulfur compounds into the air, and bacteria turn these compounds into energy through a series of chemical changes. The smell of hydrogen sulfide that would have filled the air wasn't just bad, it was the sign of a planet-wide energy economy based on sulfur chemistry. Methane was also very important for both chemical reactions in the atmosphere and biological processes. Methanogens, which are bacteria that made methane as a waste product of their metabolism, were some of the most successful organisms from this time. These organisms were so successful that they helped keep the planet warm by keeping the atmosphere rich in methane, even though the sun was dimmer. Because there was no ozone in the upper atmosphere, harmful ultraviolet radiation hit the surface of the Earth with such force that it would kill most modern life forms. This UV radiation was actually a big part of how the chemistry of the atmosphere worked, breaking molecules apart and putting them back together in new ways. The sky was a huge chemical reactor that got its energy from our young sun. Because there was no ozone in the atmosphere, the beautiful auroras we see from time to time would have been constant and much stronger. Charged particles from the solar wind could go much deeper into the atmosphere, making shimmering curtains of coloured light that could be seen even during the day. The whole sky would have been full of changing patterns of light, like a cosmic light show that went on all the time. But life wasn't just getting by in this very different world. It was coming up with new ideas at a speed that might seem impossible to people today. The genetic revolution that was going on in those old seas was making the building blocks for all living things on Earth, including us. These early microorganisms were working on the basic biochemical processes that still keep life going today, like photosynthesis, cellular respiration, DNA replication, and protein synthesis. Consider how big these new ideas are. Photosynthesis necessitated the development of highly intricate molecular machinery, adept at capturing photons and transmuting them into chemical energy. The organisms that learned how to do this didn't just make things easier for themselves. They changed the rules of life on Earth. For the first time, living things could use the sun's energy directly, instead of just using chemical energy from their surroundings. The photosynthetic machinery that developed during this time was so effective and well made that it has stayed mostly the same for 3 billion years. Plants, algae, and cyanobacteria that live today all use different versions of the same basic photosynthetic machinery that was developed in the ancient seas. This is one of evolution's most successful and long-lasting innovations. It is a biological technology that has never been fundamentally improved upon. The creation of DNA as a reliable way to store information was just as groundbreaking. RNA, or even simpler chemical systems, may have been used by earlier organisms to store genetic information. However, DNA was the first to provide information storage and replication that was both stable and accurate. This new idea made it possible for organisms to become more complex over time because reliable information storage made it possible for more advanced cellular machinery to be made. It's hard for people to understand how long these processes take. One stromatolite could be the result of thousands of years of slow bacterial growth. It took hundreds of millions of years for the Earth's atmosphere to change, from a greenhouse full of methane to one full of oxygen. By human standards, these changes didn't happen very quickly, but in geological terms they were very quick. To put these timescales in context, think about how the whole history of human civilization, from the first farming settlements to now, is less than 1% of the time we're talking about tonight. The bacterial changes that happened 3 billion years ago had more time to grow and improve than all of human history put together 1,000 times. The weather on this old Earth was very different from what it is now. Weather patterns could change a lot in a short amount of time if there weren't any large land masses or complicated ocean currents to help. Changes in the atmosphere, volcanic activity, or the sun's output could cause ice ages to start and end more quickly. There is evidence that Earth may have gone through snowball events during this time, when ice covered the whole planet, even at the equator. These weren't slow coolings like the ice ages we know about from more recent geological history. They were quick, big changes that could change the surface of the Earth in thousands of years instead of millions. We still don't fully understand what caused these snowball events, but they probably had to do with feedback loops between the composition of the atmosphere, the circulation of the ocean, and the formation of ice. Once ice started to form at high latitudes, its ability to reflect light would have made things cooler, which could have led to runaway glaciation that could freeze the whole planet in a short amount of time. The recovery from these snowball periods was just as dramatic. Volcanic activity would continue as ice covered the land and sea, slowly raising the levels of carbon dioxide in the air. The planet would warm up quickly when the greenhouse effect finally became stronger than the ice's ability to cool by reflecting light. This would happen in a geologically short amount of time, changing the world from a frozen one to a greenhouse. These climate changes weren't just interesting geological events, they were evolutionary tests that made life change, come up with new ideas or die. Every crisis killed some organisms and gave others a chance to live. The organisms that survived these planetary upheavals were very tough. They had biochemical toolkits that worked in a wide range of temperatures, chemistries, and environments. When the climate got bad, these organisms learned how to survive by going into dormant states, reproducing quickly when things got better, and being very flexible in their metabolic pathways. Some organisms evolved the ability to switch between different types of metabolism based on the environment, while others evolved protective structures that could keep them safe from extreme temperatures or chemicals. This ancient Earth had a lot of minerals, which was amazing. Erosion happened at rates that concentrated valuable elements in ways we rarely see today because there were no plants to weather rocks slowly. During this time, huge amounts of iron, copper, gold, and other metals were deposited. Many of these metals are still being mined today. These weren't the scattered, weak ore bodies that are common in later geological periods. They were concentrated bonanzas of pure mineral wealth. The well-known banded iron formations in rocks from this time tell an interesting story about the chemistry of the ocean and early life. These formations are made up of layers of iron-rich and silica-rich rock that alternate. They were made when cyanobacteria made oxygen that caused dissolved iron in the oceans to fall out. Each band shows a cycle of photosynthesis and chemical precipitation, which makes a geological record of some of the first ecosystems on Earth. The creation of these iron deposits had a big effect on the chemistry of the ocean. The oceans slowly became less reducing and more oxidizing as free iron was taken out of the water. This change in chemicals killed off many of the anaerobic organisms that had thrived in iron-rich waters and made room for new organisms that could live in or even need oxygen. It's hard to understand how big these banded iron formations are. Some formations can be hundreds of meters thick and cover thousands of square kilometers. They are the result of iron falling out of oceans that had thousands of times more dissolved iron than today's seawater. These formations hold so much iron that they are one of the biggest iron reserves on Earth. They are the raw material for a lot of modern industry. The alternating bands in these formations give us very accurate information about the chemistry and biology of ancient oceans. Scientists can see changes in the seasons, longer-term climate cycles, and even individual biological blooms that are preserved in rocks. Each band is like a picture of how the ocean was at a certain point in Earth's long history. If you're still with me on this journey through deep time, you're experiencing something that not many people think about deeply. How strange our planet's past is. We often think of Earth as eternal and unchanging, but the world we've been exploring tonight was as different from modern Earth as an exoplanet orbiting a distant star. The most obvious difference is that there are no familiar life forms. There were no birds singing at dawn, no forests rustling in the wind, and no insects buzzing through the air. The sounds of this old world would have been mostly geological, waves crashing against rocky shores, volcanoes rumbling, and wind whistling through empty spaces. But this world looked empty, when in fact it was more alive than most places on Earth today at the microscopic level. The sounds of this ancient world would have been hauntingly beautiful in their strange simplicity. Without the complicated sound-absorbing structures that plants make, every sound would have travelled farther and clearer than it does now. Wind blowing through rock formations would have made natural music on a scale that is impossible to make today. Storms on this old Earth would have been amazing to see and hear. Hurricanes and typhoons could have been much stronger than anything we know about today if there were no plants to slow down the wind or spread out energy. Lightning strikes would have lit up landscapes that were all one colour of mineral, making it look like there was an electric rainbow world for a short time. Some of the most productive ecosystems ever were the bacterial mats that covered large parts of the ocean's surface. They changed solar energy into biological energy with a level of efficiency that still amazes biotechnologists today. These organisms were also very creative in their biochemistry, coming up with metabolic pathways that are so complex and elegant that they seem like they belong in science fiction. Some of these old bacteria could change the way they metabolized based on what they had to work with. They would photosynthesize when there was light. They could switch to chemical sources of energy in the dark or in shaded areas, breaking down sulfur compounds or other minerals. This metabolic flexibility let them live in almost every niche, from the sunlit surface waters to the dark depths of the ocean floor. By today's standards, these old ecosystems had a huge range of metabolic types. There could be dozens of different types of bacteria in a single bacterial mat, and each type is best suited for a slightly different type of chemical environment or energy source. The interactions between these different metabolic pathways made biogeochemical cycles that were very good at recycling nutrients and energy throughout the ecosystem. Some groups of bacteria learn to work together in very smart ways that make it look like they are smart. Different species would focus on different steps in complex chemical changes, making biological assembly lines that could break down or make compounds that no one organism could do on its own. These cooperative networks were the first steps toward the symbiotic relationships that would lead to complex cells and eventually multicellular life. The genetic changes that happened during this time set the stage for all future life on Earth. DNA became a stable, replicable way to store information, which let organisms grow and get more complicated over time. The evolution of cellular organelles, specialized structures within cells, enabled the development of more sophisticated biochemistry and eventually gave rise to the first eukaryotic cells, the ancestors of all plants, animals, and fungi. The change from simple prokaryotic cells to more complex eukaryotic cells was one of the most important changes in evolution in the history of Earth. This change needed the creation of internal membranes that could separate different cellular functions, which made biochemistry much more complex and cells much more complex. But maybe the most interesting thing about this ancient world was that it was a place where planets were built. The cyanobacteria weren't just living in their environment, they were changing it by changing the chemistry of the oceans and atmosphere through their metabolic processes. This was the first time that life was seen as a geological force that could change the chemical and physical properties of a whole planet. The idea that life is a geological force is still changing the way we think about how planets change over time. The acknowledgement that living organisms can fundamentally transform planetary chemistry, climate, and even geology has significant ramifications for our comprehension of Earth's history and our ability to identify signs of life on other celestial bodies. The oxygen they released as waste gradually built up in the air, making it possible for more complex forms of life to grow. But this wasn't a straight line of progress. The rising levels of oxygen also caused one of the worst extinction events in Earth's history, killing off many of the anaerobic organisms that had ruled the planet for billions of years. The Great Oxidation Event was both the end of something and the start of something new. It was the end of the first great age of life on Earth, the age of anaerobic microorganisms, and it set the stage for everything that came after. Over time, the oxygen-rich atmosphere would support bigger, more complex organisms that could use aerobic respiration to make energy in ways that had never been done before. It didn't happen all at once or in a straight line when the world went from anaerobic to aerobic. It took hundreds of millions of years, and the amount of oxygen in the air changed a lot as different biological and geological processes fought for control. Oxygen levels may have been higher than they are now at some times, and lower than they are now at others. This would have made it hard for aerobic organisms that were used to living at those levels. The geological processes that shaped this ancient Earth were on a scale that is hard for humans to imagine. Many times mountain ranges grew and then were worn away. The planet's crust moved and changed shape, which opened and closed ocean basins. Volcanic activity created huge plateaus of igneous rock that would later serve as the base for continents. The tectonic processes that were going on at this time were very different from the ones that are going on now. The Earth's crust was thinner and more flexible, which made it easier for the continents to change shape quickly and dramatically. It was possible to put together and take apart whole continents in timescales that seem impossibly short by today's standards. During this time, the magnetic field that protects Earth from harmful solar radiation was probably weaker and more variable. This meant that charged particles from the sun could directly interact with the upper atmosphere, making auroras that were much more beautiful than what we see now. During times of high solar activity, the whole sky might have been filled with moving curtains of coloured light. The changes in Earth's magnetic field during this time had a big effect on how life evolved. When magnetic protection was weak, organisms on the surface would have been exposed to more cosmic radiation. This could have led to more mutations and changes in evolution. Some scientists think that these times of magnetic instability may have sped up the rate of evolutionary change. These interactions between solar particles and the atmosphere also played a role in the complicated chemistry that happens in the air's upper layers. High-energy reactions made and broke molecules at a rate that would always change the makeup of the atmosphere. This chemical activity caused the climate to change a lot during this time in Earth's history. Rivers in this ancient time were very different from the ones we know today. They carried huge amounts of sediment because there were no plants to slow down the water and stop erosion. Some ancient river systems moved more sediment in one flood than modern rivers do in decades. These sediment loads made huge deltas and alluvial fans that could bury whole landscapes under layers of rock and mineral debris. Ancient river systems looked very different from rivers today. Without plants to hold the banks in place, ancient rivers were probably much wider and shallower than modern ones. Their channels would move all the time, and during a single flood, they could move across the entire valley floor. The braided patterns that these channels would have made landscapes with amazing geometric complexity. Because there wasn't soil like we know it now, weathering and erosion worked differently. Chemical weathering, which is the breaking down of rock by chemical reactions, was often more important than physical erosion, which is what happens in most modern environments. The acidic air and rain could break down even tough minerals, making landscapes that were shaped by both chemical and mechanical forces. But even in this harsh and strange world, the building blocks of our modern biosphere were being put in place. Organisms that lived in these ancient environments came up with every major biochemical process that keeps life going today, such as photosynthesis, DNA replication, and cellular respiration. During this time, the genetic code that controls all life on Earth was standardized. This made the universal biochemical language that links all living things, from bacteria to blue whales. The fact that the genetic code is the same for all living things on Earth is one of the strongest pieces of evidence for their common ancestry. The fact that every living thing, from the simplest bacterium to the most complex plant or animal, uses the same basic system to turn genetic information into proteins suggests that this system was perfected very early in Earth's history and has never needed to be changed. The range of metabolic strategies that were created during this time was amazing. Some organisms learned how to get energy from iron, while others learned how to get energy from sulfur compounds or hydrogen gas. This biochemical research led to the development of a set of metabolic processes that life still uses today, especially in extreme environments where normal photosynthesis and respiration aren't possible. The metabolic advances of this time weren't just interesting, they were major breakthroughs that changed the limits of what kinds of environments could support life. Every new metabolic pathway was like a key that opened up new ecological niches, letting life move into places that were once too harsh for it to survive. This eventually made the biosphere bigger to include almost every type of habitat on Earth. Even though these ancient ecosystems were very small, their physical structure was very advanced. Bacterial mats were not just random groups of microorganisms. They were very organized communities with different jobs, ways to talk to each other chemically, and ways to work together that made them act like superorganisms. Different kinds of bacteria would stack themselves in vertical layers inside these mats, with each one living in the area where its specific metabolic needs could be best met. Photosynthetic organisms would thrive in the upper layers where there was light, while chemosynthetic organisms would thrive in the deeper, darker areas where they could get energy from different chemical sources. The way these layers were put together made ecosystems that were very stable and could last for thousands of years with little change. The chemical gradients in these mats were so strong that they made microenvironments that were as different from each other as continents, all in structures that were only a few millimeters thick. When you think about how modern ecosystems are always changing, It's amazing how stable these ancient bacterial ecosystems are. Modern ecological communities are always changing because of competition, predation, and changes in the environment. However, these ancient bacterial mats could keep the same structure and function for millions of years. The organisms involved had evolved to take advantage of very specific chemical niches, which made this stability possible. This created a biological economy where specialization reduced competition. The seasons on this old Earth would have been very different from what we know today. Some areas might have more extreme seasonal changes than others, and some might not have any at all because there aren't any big continental land masses to moderate the climate. The planet still tilted on its axis and orbited the Sun in an ellipse just like it does now. However, the way the climate reacted to these changes was very different because the atmosphere and oceans were very different. Some areas may have had temperature changes of 50 degrees or more between summer and winter, while others stayed about the same all year. The way rain, evaporation, and airflow worked together would have made seasonal rhythms that are very different from what we see in modern meteorology. The growth patterns of stromatolites and other geological formations show how these seasonal cycles change. Scientists can learn not only what the climate was like, but also how it changed over days, seasons, and longer cycles by looking at these old records. It's like reading a stone diary that tells the story of a planet that is no longer there. It is truly amazing how well these old seasonal records have been kept. Some stromatolites have daily growth layers that are so regular and well defined that scientists can count them like tree rings. This lets them figure out not only seasonal patterns, but also the length of ancient days and years. 3 billion years ago, the Earth spun faster, so days were only about 18 hours long. The Moon was also closer, which made tides much more dramatic than they are now. These stronger tidal cycles had a big impact on how life spread and changed over time. Stromatolites thrived in intertidal zones, which had much more dramatic changes in water level. This made it possible for organisms that could survive being submerged and exposed to thrive. The tidal mixing also helped spread oxygen and nutrients throughout shallow marine environments, which helped the complex bacterial ecosystems that were changing the planet. Because the Moon was closer, its pull on Earth's geology was stronger. Tidal forces would have made volcanoes erupt more often and the crust move around more. Some scientists think that these stronger tidal forces may have had something to do with the fast geological changes that happened during this time in Earth's history. The dance between Earth and its moon was one of many things in space that affected the weather on our planet long ago. The solar system was younger and more chaotic, with asteroid impacts happening much more often than they do now. These impacts weren't just destructive forces, they were also ways to bring water, organic compounds, and important elements from the outer parts of the solar system to the surface of the Earth. During this time, some of the biggest impact events may have temporarily sterilized large areas of the planet's surface. However, life was able to recover and recolonize these devastated areas fairly quickly because it is so adaptable and resilient. After each major impact, there were times of rapid evolutionary change as organisms adjusted to the new conditions and filled new ecological niches. The record of impact craters from this time shows that the planet was always being hit by things from space. Most of these old craters have been erased by later geological activity, but they had a big impact on how Earth evolved in the past. The heat from big impacts could have caused changes in the global climate, and the mixing of materials on the surface and below the surface could have made new chemical environments for life to explore. As we explore the microscopic world that ruled this ancient Earth, we find organisms that are more complex than we thought simple life could be. The cyanobacteria that lived in these ancient seas weren't just simple photosynthetic machines. They were complex biological systems with internal structures and control systems that were as good as those of modern organisms. These old bacteria had already changed many of the parts of cells that we think of as being more advanced. They had advanced membrane systems that could control the movement of materials in and out of the cell. They had made complicated machines for making proteins that could make hundreds of different kinds of proteins. Most impressively, they had developed complex ways to fix DNA damage, which let them keep their genetic integrity even in the harsh radiation environment of ancient Earth. The photosynthetic machinery of these ancient cyanobacteria was an amazing feat of molecular engineering. Hundreds of different proteins had to work together in very precise geometric patterns to capture light energy and turn it into chemical energy. These patterns were able to channel energy very efficiently. For 3 billion years, this biological machine has worked without any major changes. But photosynthesis was only one of many new ways that living things were using energy during this time. Other living things were also making very advanced systems for getting energy from chemical reactions. Bacteria that reduced sulfur evolved complex electron transport chains that could get energy from sulfur compounds with an efficiency that modern industrial chemists find hard to match. Methanogenic bacteria made biochemical pathways that turned simple organic compounds into methane. This added to the greenhouse gases that kept the planet warm. These organisms were so successful that the methane they excreted became one of the most common gases in the atmosphere, changing the planet's climate system in a big way. The variety of these metabolic pathways shows something deep about what life is. Life was not limited to a single energy source. It demonstrated the ability to utilize nearly any chemical reaction that produced usable energy. This ability to adapt to different environments would be very important as the Earth's environment changed over millions of years. The social behaviors of these ancient bacterial communities were much more complicated than we would expect from such simple organisms. A lot of species came up with advanced chemical communication systems that let them work together over long distances. When the environment changed, bacterial communities could spread information about the changes faster than the changes themselves. Some groups of bacteria came up with what can only be called primitive farming. Some species would grow other bacteria that made useful chemicals, turning them into biological factories that could make complex chemicals faster than any one organism could do it alone. These early instances of biological cooperation foreshadowed the symbiotic relationships that subsequently led to the emergence of complex cells and multicellular organisms. The systems these old ecosystems came up with for dealing with waste were very advanced. One species' toxic waste became another species' necessary nutrients, making closed-loop systems that reduced waste and made the most of resources. These old examples of biological recycling were so good that they made modern industrial processes look bad. Different groups of bacteria competed with each other, which led to quick improvements in both offensive and defensive biochemical strategies. Some organisms created chemical weapons that could kill other organisms, while others evolved ways to fight back against these biological toxins. This ancient arms race between different types of life led to the development of more and more complex biochemical systems. During this time, genetic transfer mechanisms developed that were very important for spreading new ideas throughout the global bacterial community. Many ancient bacteria could get new genetic abilities directly from other organisms through horizontal gene transfer, which is different from how modern organisms mostly get genetic material from their parents. This made it possible for successful new ideas to quickly spread through whole groups of people, speeding up the rate of evolutionary change. Some ancient bacteria have magnetic properties that are worth studying because they show that complex navigation systems existed long before any animals did. Some cyanobacteria had tiny magnetic particles inside them that helped them figure out where they were in relation to Earth's magnetic field. This biological compass system helped them stay in the best position for photosynthesis and find their way through the water column's complicated three-dimensional spaces. These magnetic navigation systems were so finely tuned that they could pick up changes in the strength of the magnetic field that modern scientific tools would have a hard time picking up. The biological processes that let these bacteria make and organize magnetic particles in their cells were very advanced and involved complicated biochemical pathways that scientists still don't fully understand. The evolutionary pressure to create these navigation systems shows how complicated ancient marine environments were. The ancient oceans were not simple, uniform places. They had complicated gradients of light, temperature, chemistry, and nutrients that organisms had to carefully navigate in order to survive and thrive. As we look at these old seas tonight, where are you listening from? The iron atoms in your blood may have once been part of the magnetic navigation systems that ancient bacteria used. They have been recycled through billions of years of planetary history. Viruses played a part in these old ecosystems, which makes it even harder to understand how life began. Viruses were already around 3 billion years ago. They infected bacteria and helped new genetic changes happen by moving genetic material between different organisms. These old viral infections weren't just sources of disease, they were also engines of evolutionary change that sped up the development of new biological abilities. It was hard for ancient bacteria and their viruses to get along. Viral infections could kill individual bacteria, but they also made it possible for bacteria to exchange genetic material, which helped bacterial populations adapt more quickly to changes in their environment. This old dance between hosts and parasites set up ways for living things to interact that still affect evolution today. Some scientists think that viruses may have been very important in the evolution of DNA as the main genetic material for life. The need to protect genetic information from viral attacks may have led to the development of more advanced DNA repair systems, which eventually led to the stable genetic systems that are found in modern life. There were more than just bacteria and viruses in the oceans of the past. There were also more complex organic structures that were at the edge of living and non-living things. These early life forms may have been important steps in the evolution of cellular life, giving scientists a way to try out different ways of organizing living things. Some of these old organic structures were like biological labs where scientists could try out and improve different chemical reactions. The reactions that worked best would be used in living things, and the ones that didn't work would be thrown away. This trial and error method of coming up with new biochemical ideas was very wasteful by today's standards, but it worked very well to come up with new biological ways to solve environmental problems. The fossil record from this time not only has the remains of organisms, but it also has chemical traces of their metabolic activities. These molecular fossils, also known as biomarkers, give us a lot of information about ancient ecosystems that we couldn't get from regular fossils alone. By looking at the kinds and amounts of different organic compounds in old rocks, scientists can figure out how living things used to work in the past. Some of these molecular fossils are so well preserved that they still have information about how ecosystems changed with the seasons in the past. Scientists can find out not only what kinds of organisms were there, but also when they were most active, what they ate, and how their numbers changed over time. You can look at detailed ecological surveys of ecosystems that existed billions of years ago. To keep these molecular fossils, very specific conditions had to be met. This tells us something important about the environments of the past. To keep these chemical signatures from breaking down, organic matter had to be buried quickly in sediments that didn't have any oxygen in them. This suggests that ancient marine environments had places where sedimentation happened quickly and oxygen levels dropped, which helped preserve fossils very well. Isotopic analysis of preserved organic compounds shows how chemically complex these old ecosystems were. Different metabolic processes leave behind unique isotopic signatures that can be found billions of years later. Scientists can use these chemical fingerprints to figure out not only what organisms were there, but also how they were living in their old environments. For instance, sulfur isotope ratios can show if ancient bacteria were using sulfur-based metabolism, and carbon isotope patterns can show if different types of photosynthesis were happening. Nitrogen isotope signatures can tell us about how nutrients move around and how available different nitrogen compounds are. Each part of the story about how these old ecosystems worked is told by a different part. The worldwide spread of these isotopic signatures shows that many of the basic biogeochemical cycles that happen on Earth today were already in place 3 billion years ago. The cycling of carbon, nitrogen, sulfur, and other elements through the biosphere was already a planetary scale process driven by the metabolic activities of ancient microorganisms. As we get closer to the end of our journey through this ancient world, it's a good time to think about what we've learned about our modern Earth. The planet we live on seems stable and good for life, but it has actually changed slowly over billions of years, with big changes that changed everything from the chemistry of the oceans to the makeup of the atmosphere. 3 billion years ago, the organisms that lived were not just simple ancestors of modern life. They were advanced biochemical engineers whose work made all later life possible. The air we breathe, the soil that grows our food, and the mineral deposits that power our technology are all gifts from those ancient microbial communities. Knowing about this long history also helps us understand the changes that are happening to the environment right now. Earth has gone through some very big changes in the past, some of which were much worse than what people are doing now. But life has not only survived these changes, it has often become stronger and more diverse than it was before. This doesn't make taking care of the environment any less important today, but it does remind us that our planet is stronger and more adaptable than we sometimes think. Biological innovation, chemical cycling, and planetary feedback systems are still at work today, just in different ways because of the complex ecosystems that have developed over geological time. The story of Earth 3 billion years ago is really a story about change and what could happen. Life not only survived, but thrived in conditions that seemed impossibly harsh and alien. It did this by coming up with new ways to live and adapt, which eventually led to the rich, complex biosphere we know today. Every tree, animal, and breath of air that is rich in oxygen is proof that those ancient microbes were successful. This ancient world has left a legacy that goes far beyond the biological world. The chemical reactions that happened in the oceans and atmospheres of the past set up the geochemical cycles that still control the chemistry and climate of Earth today. The mineral deposits that formed during this time are what most of today's technology is made of. The iron precipitation processes that happened in ancient seas may have even changed the magnetic field that protects us from harmful cosmic radiation. It is very important for technology to understand these old biological systems. Modern biotechnology is increasingly looking to ancient organisms and metabolic pathways for ideas on how to make new industrial processes. Extremophile bacteria that live in places that are like those that existed 3 billion years ago are helping us understand how biological systems can work in ways that would destroy normal technology. Some of the most exciting new ideas in renewable energy technology are based on biological processes that were perfected billions of years ago. The photosynthetic machinery that evolved in ancient cyanobacteria is the basis for artificial photosynthesis systems that could provide clean, renewable energy. Biological fuel cells that could power anything from spacecraft to medical devices are based on the electron transport systems that ancient bacteria used to get energy from their surroundings. Our understanding of Earth's ancient biosphere also has a big impact on the search for life on other planets. The types of places that could have supported life on early Earth, high radiation, extreme chemistry, and changing temperatures, are like the kinds of places that could exist on Mars, Europa, or other worlds in our solar system, and beyond, that might be able to support life. We can better understand what signs of life might look like elsewhere in the universe by learning how life worked on Earth under these conditions. The atmospheric signatures that ancient life on Earth left behind can be used to find signs of life on other planets. The oxygen and methane that ancient ecosystems made mix together in ways that are thermodynamically unstable without life. Similar atmospheric imbalances on faraway planets could mean that biological processes like those that happened on Earth long ago are still happening. As you fall asleep tonight, you might dream of those old seas, full of life that you can't see, under skies painted in colours that don't exist anymore. You could picture walking on shores made of pure mineral crystal, breathing air full of greenhouse gases, and seeing stromatolites grow in real time under the light of our younger, dimmer sun. These dreams aren't just flights of fancy, they're links to our deepest roots, reminders that we are all children of that ancient world, carriers of genetic information and biochemical processes that have been perfected over 3 billion years of planetary evolution. In a very real way, those ancient cyanobacteria are still alive in us, in the cells that make every breath, heartbeat, and thought happen. The mitochondria in our cells are the descendants of bacteria that learned how to use oxygen to make energy. The chloroplasts that let plants photosynthesize are related to the cyanobacteria that first learned how to use sunlight. Even the ways that our DNA repairs itself can be traced back to the molecular systems that ancient organisms used to deal with the harsh radiation environment of early Earth. 3 billion years ago, the Earth may have seemed like a strange place, but it was where the basic processes of life were made. Knowing about this old part of our planet's story doesn't just satisfy our scientific curiosity, it also connects us to the deep time that shapes everything we see around us, from the rocks under our feet to the stars above our heads. The atoms that make up your body have been a part of this planet's story since the beginning. The carbon in your cells may have come from carbon dioxide in the air a long time ago. The iron in your blood may have come from old oceans that were full of dissolved metals. The oxygen you breathe is the result of billions of years of photosynthesis that started in those old bacterial mats. This atomic recycling links you to the history of life on Earth and to the cosmic processes that made the elements themselves. The nuclear furnaces of ancient stars made the heavier elements in your body, and supernova explosions spread them throughout the galaxy. The hydrogen in your body is as old as the Big Bang. You are literally made of star stuff that has been put together over billions of years of planetary evolution. The story we've talked about tonight is only one part of the much bigger story of how the universe has changed over time. The same physical and chemical processes that formed Earth 3 billion years ago are still going on in the universe, and they could create life in places we can't even imagine. Our ancient Earth is a model for how these things work, and a reminder of how creative and strong life is. The future evolution of our planet will undoubtedly bring changes as dramatic as those we have explored tonight too. In the long run, the sun will get brighter, the continents will move, and life will change and adapt to new situations. In a few billion years, Earth might become an alien world again, changed by things we can only barely picture. But the basic rules that governed life 3 billion years ago, being able to get energy from the environment, reproduce and evolve and adapt to changing conditions, will still be in place, no matter what forms life takes in the future. As our planet moves through deep time, the creativity and strength that helped life thrive in what seemed like hostile conditions on ancient Earth will continue to find new ways to show themselves. Good night, time travelers. When you sleep, you're part of the same cycles of energy and matter that have kept life going on this amazing planet for billions of years. This connects you to all living things today and to the ancient world that made all life possible. Your story is also the story of Earth 3 billion years ago, written in the atoms of your body and the biochemical processes that keep you alive. You have the legacy of 3 billion years of evolutionary change inside you. You also have the wisdom of many generations of organisms that learned how to survive in a world that was always changing. You are the most recent chapter in a story that started in those ancient seas and will continue long after our current forms of life have died out and new forms of creative power have appeared on Earth.